Checking YouTube. Let's put the link and the ting and the ting and the ting. And here, the audio is horrendous. Horrendous audio. Uh, unplug. Replug. Okay. Oh, it should be good. Just that there's a delay. Okay. Let's check the volume. Volume is okay. Everything looks okay. This is okay. This is okay. This is okay. This is everything looks okay. Yeah, everything looks good. It looks fine. All right. Two people. Why is there two people? Okay, let's. I just wanted to finish listening to her. Let's listen to her. Let me just turn this off. Enough of that.
Locally. Well, no one's ever said that we can't have waves that go two paths in a local hidden variable. Both paths, and on this output, the wave interferes destructively with itself, so no signal, and all photons. The wave
Okay, I
can
don't know what she's talking about.
If lambda is 1, then the
So hold on. I'll be right with her. 1 second. A message just came in. Mm. Mm. Okay. So let me see what I can do about this. I just want to see today's. I want to see my stream on YouTube. So I go to YouTube, and there's no way I can see it. I go to the live. I click on the live and it doesn't respond. This is usually an issue. Like you cannot click on the link um, when in the first couple of hours. So the link usually doesn't work, which is always a good thing. Okay, here it is. Maybe
The link usually doesn't work.
Okay,
Which
so
is
it's
always
fine. It's fine. It's fine. There you go. We're done. All right, let's continue listening.
photon goes that way. If lambda is 3, then it goes the other way. Why 3 and not 2? Because I know what's coming next and you don't. Now we put two mirrors here and here so that the photons don't run off our screen, and another two semi-transparent plates there. Okay, so now we have 4 different paths, each with 25% probability. We'll give those the numbers 1, 2, 3, 4. And now we'll combine these two paths by directing both towards the same beam splitter. If our hidden variable explanation was correct, then we should get half of the photons here in detector A and half here in detector B. But this isn't what
Notice that whoever does the animation got A and B, of course, mixed up.
happens. Indeed, you have probably noticed that this setup is what's called a Mach-Zehnder interferometer.
Never heard of a Mach-Zehnder interferometer.
If the paths are the same length, then the photon will always
Same length means it's a square.
go to detector B.
Why would they always go to detector B? What is unique about detector B? It seems like it should be symmetric.
You can measure it and all. It's definitely real.
What do you mean? This doesn't make any sense. Why would it choose B over A?
The interference in these detectors is exquisitely sensitive to the length of the paths.
You said they're equal.
Which is why one can use this type of interferometer to measure tiny deformations. This is how a gravitational wave interferometer works. But how
Gravitational wave? Okay.
does it work? Well, in quantum mechanics, the photon is described by a wave function, and waves can interfere with themselves, either.
Why do you bring up the fact that a photon is described by a wave function? I don't need to know that a photon is described by a wave function. It's like telling me my mass is described by Newton's F equals ma. That's like that's irrelevant. F equals ma is useful for something. The Schrodinger equation is useful for whatever things it is, but a particle wave is a particle wave. It is what it is. Why do I care that there is ways to describe it mathematically? Why do they keep bringing up Schrodinger's equation? There is a photon. There were photons before there was Schrodinger's equation. Why do I care for Schrodinger?
Constructively or destructively. In quantum mechanics, the photon goes over both paths, and on this output, the wave interferes destructively with itself, so no signal, and all photons go the other way.
Wait, hold on. So you're saying that the photon wavelet, I call it a wavelet. It's really just a wave. There's nothing special about, I was thinking about this today, there's nothing special about quantum mechanics that a photon is a wave, and it's a wavelet. Like, what is a wave? If you think about it, what is a wave? Is a wave infinite? No, of course a wave is not infinite. Every wave is finite. All right, well, congratulations. That's quantum mechanics. That's all it is. It's just a finite wave. Now there is a little bit distinction. And that is that this wavelet can never become, it can't really become two halves. Somehow it's always maintaining its integrity. It's an integrated, it's always integrated. So even if it splits, when it's detected as one photon with the same energy that it had originally. So I don't know how that works. That I honestly don't know yet. Anyway, so she says, well, it splits. It's a wave. I don't care about the wave function. The wave function just describes the way it behaves, which we can know intuitively. Because it's a wave, because we've seen it behave. We know how these things behave. We've seen photons behave in different circumstances, different experiments. We know how they behave. They behave in like wavelets, like finite waves. So when they go through a partial mirror, a beam splitter, they're both going to go through and reflected, and then get reflected and reflected, and by the time they get here, It's symmetric. I don't see the difference. It's symmetric. Why would it choose to go this way but never this way? So it always cancels out this way, but it never cancels out this way? Why?
But the price you have to pay for this is that if you measure which path the photon went, you need the non-local collapse. How can we use hidden variables to get this done locally?
I don't know what she's talking about. Now I'm lost. I just don't understand her description.
Well, no one's ever said that we can't have waves that go two paths in a local hidden variable model. All we need to do is say, if we measure which path the photon goes, then we use these variables, 1, 2, 3, 4, and the photon behaves like a particle. If we measure the interference between the paths, then that's hidden variable number 5. The photon behaves like a wave and goes only into detector B. Problem solved. It's local because the photon goes on one continuous path into the detector where it's measured. For this to work, the value of the hidden variable that determines what the photon does must depend on what you measure.
At this point, I'm not following her.
It's called a violation of measurement independence. So the lesson is, if we want a local hidden variable model that reproduces quantum mechanics correctly, then it needs to violate measurement independence. This finally brings us to Bell's theorem. I'm not going to explain Bell's theorem because you've already watched 20 videos about it and it didn't help. I'll just tell you what it says. Bell's theorem says...
We need to look into the Mach-Zehnder. Okay, let me look into Mach-Zehnder. Mach-Zehnder interferometer. This is too much. 4 years ago, educational documentaries.
Everybody to our class Introduction to Quantum Optics. Today we want to make a small interlude and
yeah, they're not going to talk.
This is the Mach-Zehnder interferometer, what has been explained by Benjamin Schumacher in his TTC course of the physics of the...
I don't know what he's saying.
Hi there. Today we're going to talk about the Mach-Zehnder interferometer. Get ready. Hi there. Today we're going to talk about the...
So he has an introduction longer than the video.
Mach-Zehnder emitter. The Mach-Zehnder interferometer is a system of 2 detectors and 1 emitter. The emitter runs through a polarizer, and the polarizer causes there to be a beam.
Oh, she didn't mention that there's a polarizer. But first there's a splitter, then there's a polarizer.
50% this way and 50% this way, or a split. These beams are then bounced by a mirror up to another polarizer, and I'll let you think about...
Well, there's another polarizer? What's going on? So, okay.
Is there going to be a 50-50 split between the 2 detectors, or is it going to be something a little bit more complicated? If you remember anything about superposition, it's almost like a particle forgets, a fundamental particle, forgets what state it was measured in previously. Forgets, a fundamental particle, forgets what state it was measured in previously. And if we add a piece of glass here, delta phi, we end up with a little bit of refraction as the light runs through, and we end up with an oscillation effect. So as the light is detected in the detector 1, or the first detector, it goes down, but the inverse is found in detector 2. We can explain this using some simple formulae in regards to our piece of glass here. So if we were to take E1 plus E2 and add in our piece of glass here, EI delta phi, the next one, the other detector, would need to be a minus. Always keep this in mind. All right, so really quickly, I'd like to talk about polarization of light. This might seem a little bit off topic, but this might help you out as well. So unpolarized light in a 3-dimensional space, imagine that the lines here are going everywhere for the blue, and the purple is maintaining maybe a constant, or they could also be flipping or rotating. So unpolarized is a very wild state of light, whereas circularly polarized can be left-handed or right-handed, typically left-handed. and it's the direction in which it spins as it travels through space. Linearly polarized means that it is pretty much lined up. So both the momentum and the other factors play in, and they are together. So if we have
I don't understand what they're talking about.
polarized light hitting another polarizer, what do you think is going to be the result? We've polarized it.
I mean, these topics are so complicated, and instead of explaining, they just assume everyone understands. I mean, the math is impossible to understand, and the diagrams are impossible to understand. It's like you have to live inside these ideas in order to follow a 3-minute video.
Maybe it's linearly polarized or maybe it's circularly polarized. You should definitely check that out in your books. Let's get back to this interferometer and superposition. So we remember during our talks about the Heisenberg uncertainty principle that when you measure one property of a quantum state or a quantum particle, and you measure it again, the first state is kind of forgotten or dropped. You cannot measure two different measurements, or you cannot
Could you give us a link? Because I don't know what you mean.
measure two different states of a particle at the same time. Only one can be measured. So the same thing happens here to our
Why is that? Can you explain that mechanically?
light as it runs through, and we end up with a complete oscillation between our two detectors. Now, when you get into this equation, just remember that this is wave in electrical mathematics. Don't get too excited. It's not too bad. So why do we use electric? Because light is electromagnetic. So electromagnetic force, light, hence wavelengths and electric formulae. If you have any questions, please drop them in a comment below. I'll be glad to answer
That
any of
was
your questions.
completely
Have yourselves a
useless.
beautiful day. Don't forget to like.
Another person who explains Heisenberg uncertainty principle. All right, so we need more explanations.
Hi.
Hi, welcome back. Let's do some more interferometry. The Mach-Zehnder interferometer has two inputs and two outputs. Light from one single source is emitted into the interferometer. A beam splitter splits the light from the source into two different paths. These two paths then recombine light later via a second beam splitter. Here we can have two screens or two detectors to study the interference. The reason why this interferometer has two paths is to compare the light following each path and study the differences that you can place between both paths. For example, imagine you want to measure the index of refraction of a gas. You would put two identical cells, one in each path. To one of them,
Do you want to tell me that if you fire, that you can have an experiment where you light this laser and you end up detecting either this or this? I don't believe it. Show me.
you would remove slowly the gas to observe the shift in the fringes on the screen.
What?
Last to observe paths. Imagine you want to measure the index of refraction of a gas and study the differences that you can place between both paths. For example, second beam splitter. Here we can have two screens or two detectors to study the interference. The reason why this interferometer has two paths is to compare the light following each path and study the differences that you can place between both paths. For example, imagine you want to measure the index of refraction of a gas. You would put two identical cells, one in each path. To one of them, you would remove slowly the gas to observe the shift in the fringes on the screen. Light following both paths goes through two full beam splitter, independently of which screen it'll end up hitting.
I don't understand his English. I don't know what he's talking about. Hidden, hitting, what? Hitting.
Hello, we are a group of students that are taking quantum chemistry for
Okay.
Mach-Zehnder interferometer with polarizing beam splitter. Polarizing beam splitter cube splits the polarized light into two beams which are orthogonal to each other. The horizontal light beam
Now check messages.
is transmitted and the vertical light beam is reflected. This is the polarizing beam splitter cube. This dot indicates that this side is for light beam input. This side is to output for reflecting vertical beam. And opposite side is to output for transmitting horizontal beam. I am setting the polarizing filter to horizontal at the transmitting side and setting another polarizing filter to vertical at the reflecting side. The transmitting
This is too much. Okay. Good animation, of course, no talking aloud. Okay. Why does it go only in that direction?
This is a Mach-Zehnder interferometer. It consists of a half-silvered beam splitter, where incoming light is split between two paths. These two paths then lead to another half-silvered beam splitter, where the light is recombined. The path length of each arm can be adjusted by moving the associated mirror. When we adjust one of the path lengths of our Mach-Zehnder interferometer, we can see that the distribution of detections between our two detectors changes. If light is made of particles, why would this happen? Each particle should go down a path and just get randomly split again at the final beam splitter. If light is a wave phenomenon, however, this path length difference will impart a phase shift. This phase shift changes the way the waves recombine at the second beam splitter, shifting whether or not the light is constructively or destructively interfering. Our photon can't be explained.
Okay. Very nice animation. I have no idea what they're talking about.
Hey crazies, back in 1959, two physicists published a paper in the Physical Review. They suggested that maybe we've been imagining the electromagnetic field all wrong. They even outlined an experiment to prove it. An experiment that almost broke locality.
Well, at least it pronounces experiment correctly. Most people say experiment, even though it's spelled experiment. 1 second, let me read a message. Very nice. La 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 la. Okay, how long? We've been here for 24 minutes and I'm losing my mind. I think I'm losing my mind. Let me text her. Okay, let's check the audio. Very good. Very good.
Episode was made possible by generous supporters on Patreon. Okay, first order of business. What the heck is locality? It's easily one of the most important principles in all of physics. It states that the behavior of an object or particle should only be influenced by events or phenomena at the location of said object or particle.
Very good. That's a good definition.
The universe is inherently local. In other words, for two things to affect...
I wouldn't say the universe is inherently local. I would say that's the assumption. That is the scientific assumption. If there is a scientific assumption, the assumption on which science is based on, that is locality. That there's no spooky action at a distance. 1 second, I have a message. Let's see. Yeah.
each other, they have to be at the same place.
Very good. I would say, I would use gravity as an example, but they don't understand gravity, so they can't use gravity as an example. So maybe they can use light, but it's a very weak example because everybody agrees that light must come from a source. But gravity, they feel gravity is spooky action at a distance. So for them, they actually believe in spooky action at a distance.
It's kind of a big deal. And not like Big Deal Clone, like an actual big deal. Hey! Anyway, most forces require physical contact to work.
Most forces. Let's see what he does with gravity.
Things have to touch each other.
Yeah, so how do you deal with gravity?
But even before quantum mechanics came along, we knew this locality principle had a few notable exceptions. Gravity being the most obvious.
There you go. Oh my God. So they believe in locality with the exception of gravity. Oh my God. And that's the end of science. Thank you very much, ladies and gentlemen. Science was very nice while we had it. Very nice. Unbelievable. How do these people wake up in the morning and put on their pants without shooting themselves in the head? I don't know. Honestly, I just don't know.
It seems to be able to reach out over unimaginable...
And he doesn't know. They don't know. They don't know. It's staring them in the face. But they gave up any notion of ether, so they don't understand how it works. How unfortunate. Oh, I thought Einstein explained GR with curvature. It curves space-time. The curvature of space-time. Say it.
Imaginable distances. It makes this squirrel fall near the surface of the Earth. But it also keeps the moon in orbit around the Earth, and the planets around the sun, and the stars inside the galaxy. Which, seems a little strange.
He's going to say Einstein explained it through curvature of space-time.
But rather than give up on locality, we consider the possibility that maybe that effect isn't direct. Instead of the Earth affecting this rock, maybe the Earth does something to space, and it's the space that affects the rock. It's something we call a field, a number.
Okay, it's good, but he doesn't. It's a number, you see. They live in a mathematical universe, these people. They live in a magical universe. They replaced God and angels with mathematics, which is basically the same. It's an unintuitive, either way, it's an unintuitive universe. It's a universe that we cannot understand. It's a universe that is magical. And that's why they treat math basically like magic and mathematicians and scientists basically like clergy. And they have this reverence. Trust the science. That's why the Covigi was such a big deal, and that's why the global warmingation for them is such a big deal, because you have to believe the clergy. Believe the clergy. Yeah.
or set of numbers assigned to points in space.
Yeah.
In classical or Newtonian physics, that field is made up of arrows called vectors.
So what did Einstein add?
In general relativity, it's made up of curvature tensors.
No. General relativity must reduce to Newtonian gravity. So that's completely that. I don't care anyway. Either way, it's the ether. The ether annihilates. That's the nature of the beast. The ether annihilates when it impacts, when it is in the vicinity of a massive object. And when it annihilates, a vacuum is created. And there is a positive pressure in the universe of the ether, so that when the ether annihilates near Earth, so you have a layer that is annihilated, so low pressure ether. There's low pressure ether, and this causes the high pressure ether to flow into the low pressure. So you have the flow of an actual something. Actual matter is flowing. And things that are in the way, like the moon, get dragged in. That is gravity. And the apple that is in the way gets dragged in. That is gravity.
But it's still a field. It's a number or set of numbers assigned to points in space.
No, it's not. That's not a field. That's magic. A field is something. There is something there. It's called the ether. It's actual particles. Unlike us, we are just waves in the ether. The ether is the only thing that is real.
Isn't that a little mathematical? Yeah.
Well, at least he admits it. And that's why he calls himself crazy.
Yes, but so is everything else in physics.
Oh my God, so that's it. Physics is mathematical. Physics is mathematical. It's not physical, it's mathematical. Congratulations. Well, now we know. What are all these messages? Jesus. What is that? Oh, what? Anyway.
Lots of mathematical things represent something real.
Wait a minute. So it's representing something real. So there is something real. Oh my God. What is it?
For example, we represent motion with a velocity arrow. The motion is real. The velocity arrow is not. It's the math that represents the real thing.
Okay, so yeah, go on. So what is gravity? And all this, he's trying to explain the Mach-Zehnder interferometer, and he's no joke. This guy is he's a tough guy. He knows his physics.
The same is true for the gravitational field. I mean, it's not like my hand is hitting a bunch of arrows right now.
Oh, okay. So what is it? What is it hitting then?
But locality says the Earth can't affect this rock directly.
So how does it affect it?
So the force must be due to something where the rock is.
Very good. So what is it that is there?
We call that a gravitational field.
Yeah, but that's still a mathematical concept. That's just a description. What is actually there?
And represent it with a bunch of arrows.
Yeah, that's the representation. Yeah.
It's not a substance or a fluid or anything.
Oh, it's not a fluid. It's not a fluid. All right, okay. If it's not a substance or a fluid, then what is it? You're talking about locality. But you're describing spooky action at a distance. And what about the curvature of space-time that's supposed to explain gravity? Why aren't you talking about that?
But it's something. Something is there.
But it's not a fluid or a substance, but something is there. What is there?
And whatever it is, it preserves the principle of locality.
What? What do you mean preserves? What do you mean? Explain then I don't understand how you understand locality. What do you mean it preserves locality? You're saying it's not a fluid, it's not a substance, so there's nothing there. So what is it that is preserving? There's nothing there.
The Earth creates a field, and it.
Oh, the Earth creates a field. What? The Earth creates a field? What do you mean the Earth? So the apple? Then I don't understand. What do you mean it creates? I don't know what that is. What do you? What, I don't understand. I'm sorry. I'm sorry. I'm too dumb. I'm too dumb to understand.
It's that field that affects the rock. We can very easily extend this concept to electricity.
You're gonna extend the concept? What concept? This is a non-concept. This is the most. How do you people live with yourselves? Oh my God, these people are so confused on the fundamentals, on the simplest fundamentals. They still don't understand gravity. Oh my God.
And magnetism. Charges don't affect each other over a distance. One charge creates an electric field.
Oh, the charge creates a what?
Charges don't affect each other over a distance. One charge creates an electric field.
One charge creates an electric field? It didn't look like the field came out of the charge, according to you. Look at that.
Charges don't affect each other over a distance.
So I'm going to do this in steps.
One charge.
There you go. It doesn't look like the charge is creating the field in your animation. It looks like the field is creating itself. It's coming to a being. It's coming into existence all by itself, everywhere, all at once. That doesn't sound like the charge is creating the field. The charge is not creating the field unless it's like it's creating it from the distance. And then again, it's spooky action at a distance. You keep bumping your head against spooky action at a distance. Unbelievable. Unbelievable.
Creates an electric field, and that field affects the second charge. Magnets don't affect each other over a distance either. One magnet creates a magnetic field.
Oh my God. The magnet creates a magnetic field. It creates a magnetic field. So before it created the magnetic field, there was nothing there. There was empty space. So you should be able to detect this field, but your animation didn't say that. And what do you mean the magnet creates the magnetic field? So it should be losing something. If something is coming out of the magnet, then something is coming out. It should be losing mass.
And that field affects the second magnet.
How?
Locality is preserved.
Oh my God, locality is preserved. It's just like he's asserting locality is preserved. Locality is the notion that the universe is mechanical. Why is he looking to the side? Locality is the notion, is the assumption that the universe is mechanical, that anything in the universe can only influence whatever is right next to it. And you have to be able to explain any phenomenon in the universe through some chain reaction, that I can only influence something that is right next to me, and maybe that thing influences something that is right next to it, and so on and so forth. That is locality. That is the locality assumption.
Or is it? In this video, we learn that the behavior of a particle is described by a wave, something we call a quantum wave function. I also mentioned that that wave is unobservable, and that's true, it is. But if we have two particles, we might be able to see a difference. This wave?
It's hopeless. I'm supposed to learn from these people that, honestly, there's no way they understand anything. There's just no way. These people are lying. They're lying through their teeth. Okay, 1 second. We have someone talking to us. Where? That experiment is just interference. The polarizers are used to make the waves be collinear, so you get clean interference. Physicists just complicate things too much. One path you get destructive, the other you get constructive. It's like that by design. But they're symmetric. Why is one different? I don't know. I mean, I don't understand. Let's see what he says. Why don't you join us? Okay, let's wait for his response. Let's continue listening.
Could have started here, or even here.
1 second. Oh, you cannot join now. Okay. Okay. We'll wait for his messages.
Here. As time plays out, you can see these waves are out of sync. We say they're out of phase in time. But all three of those waves describe the same particle. It's something we call global phase invariance.
Wow. Talking about confusion, I never heard of this term, global phase invariance.
You want the wave to start here instead of here? Quantum particle don't care. The probabilities you
What do you mean start here instead of here? I didn't understand that.
calculate from that wave function will be the same regardless. But back in 1959, two physicists proposed an experiment that calls everything into question. Say we've got a device that emits electrons that are all in phase. That means their waves are all synced. If we separate two of those electrons and then bring them back together, they should still be in phase. And that's exactly what happens when we do the experiment. We get a pattern on a detection screen that is consistent with two waves in phase.
Come to think of it, okay, so, wait, what?
Still be in phase. And that's exactly what happens when we do the experiment.
Wait, it's a single electron that splits in two? What?
That emits electrons that are all in phase. That means their waves are all synced. If we separate two of those electrons and then bring them back together.
What do you mean separate two of those electrons? How do you create two electrons? I don't understand. Is it one that becomes? I see that he's firing two at a time.
Together, they should still be in phase. And that's exactly what happens when we do the experiment. We get a pattern on a detection screen that is consistent with two waves in phase.
Two waves in phase. What do you mean two waves in phase? This is two waves in an interference pattern.
Wait, what's that screen made of? What kind of electron device? How are you separating the electrons? None of that matters.
Yeah, none of that matters. And also don't show us the experiment, always animations. Animations are the best. We don't need to see anything. Nothing to see here. Okay, I'm becoming a little bit hungry.
Don't get hung up on unimportant details.
Oh, unimportant. Oh, yeah. Conducting experiments, because he's not an experimentalist and he doesn't know. I have to assume he never conducted this experiment. He never went into a lab and saw it. I have to assume that.
All that matters here is that they're in phase at the end. How we got there is completely irrelevant. Okay, so we get a pattern on a detector screen that is consistent with two waves in phase.
What do you mean two waves in phase? I don't know what you mean by two waves in phase. These waves are in phase and out of phase. It's called an interference pattern.
It's fine so far. No problems at all. Now, let's consider a second device called a solenoid. That's just a long, densely packed coil of wire. Nothing too fancy. If we run an electric current through that wire, we'll get a magnetic field, but only inside the coil. Outside the coil, the field is so weak, you might as well just say it's zero. Things start to get weird when we use this coil in our experiment. Say we place the coil in the middle, so the two electrons go around the outside. There's no field out there, so the principle of locality says they shouldn't be affected. Things should only be affected by other things at their location. Except those electrons are affected. We get a different pattern on the detector screen. The electron waves are out of phase. What? I know, right? Somehow, the magnetic field here is affecting electrons all the way out here. That shouldn't be possible. So do we finally give up on locality then? Not so fast. This phase effect is called the Aharonov-Bohm effect, after the two physicists who proposed the experiment. Thankfully, those same two physicists, also proposed a solution. What if there is something in the space the electrons are passing through? We know there's no magnetic field, but maybe the magnetic field isn't the best way to look at this. In basic mechanics, you normally use forces and Newton's second law. That's where electric and magnetic fields are.
But the electron is a wave, so at least part of this wave is traveling inside the solenoid and is influenced by the magnetic field. One second. Okay, this is a completely different experiment. Basically, they found the curl is a real thing and affects spin. Are you live with us right now? I don't understand. Are you live with me right now? Are you watching? Or are you? Oh, okay. 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 So you're saying. So this is a completely different experiment. Oh, it's not the Zender? The Zen-Schmend? This is not the Zender? Oh, this is not the Zender? Oh, okay. Let's, okay, I'll finish watching this. I'm hungry and tired, as always.
The most useful. An electric field is a force per unit charge. It tells you how much force could be exerted on a charge at that point. The magnetic field does the same thing for magnets and moving charges. The two of them...
One second. But you can see, okay.
Together allow us...
How easy it is to affect the spin of an electron. Why don't you write? It would be easier, I think, if you wrote in the thing, in the chat, in the YouTube, how easy it is to affect the spin. Kind of tells you a bit about the Stern-Gerlach, or without the name, whatever the name is. Yeah, the Stern-Gerlach. I don't know. I don't know what to say. I don't know what to say, honestly.
To find an electromagnetic force. But forces are not the only way to look at a situation. Sometimes energy and momentum can give you a deeper insight. Take this battery, for example. It has a voltage of 1.5 volts, and a volt is just a joule per coulomb, an energy per unit charge. What that means is the energy at the positive end of the battery is 1.5 volts higher than the energy at the negative end of the battery. That number isn't just limited to those two locations, though. This battery assigns a number like that to every point in space. It's something we call the electric potential. And since that number is assigned to every point in space, it's a field, a scalar field. This number tells us the energy that 1 coulomb of charge would receive from the battery at each location in space. However, the solenoid in our experiment doesn't have an electric potential around it. It has a magnetic potential, which fulfills a similar purpose, but for momentum instead of energy. Since momentum is a vector, so is the magnetic potential.
Okay. So the vector, the canonical momentum, QA, magnetic potential. This is momentum, it's MV, plus QA. What is A?
Which is why we call it a vector potential. We have one of these magnetic potential fields around our solenoid.
Okay, so before he said there's nothing, now he said there is. Is it measurable? Right, we know, right? Science says if it's not measurable, then it's not scientific. Is it measurable? Is there any way to measure this thing? Same goes for the battery. Whatever he said about the battery, I don't know. Can he show that? That's why I need you to show us experiments. I don't know what you're talking about. You said before there is no field. Now you're saying there is a field. Why is it rotating that way? This is the right-hand rule. So there is a field. I don't understand. Then what's the question?
And it solves our locality problem.
Wait, who said? Okay, so there is a field. So that's the problem. So, okay. Okay. Carlos Paiva says, that's the curl. This experiment, in fact, detects it. I don't know. I don't know what's going on. This experiment is, I don't know. I'm looking for the Mach Zehnder.
Electrons in our experiment pass right through the magnetic potential, and it predicts the phase difference we see on the detection screen.
Okay, so there's a phase difference. I didn't get it, the thing with the solenoid. So before you had this wave, now you have that wave. It looks like something changed with the interference. So what did anyone make the prediction that this is what will happen because of the solenoid? What would happen? What does the solenoid do? I don't understand what it's doing. 1, 2, like the number of lines is different because over here you have 2 on the outside, 2 on the outside, and 1, 2, 3, 4, 5, and here you only have 4. So I don't know what's going on.
So locality, it's kind of a big deal.
I don't get it. I honestly don't see it.
Things should only affect other things at their location. It's a principle that we see obeyed over and over and over again. If you want to affect something over a distance, you have to send something between you and that thing. Maybe that exchange happens because of a physical object. Oh, ow! Maybe it happens because there's some kind of field. But no matter what, even in weird quantum experiments like this one, there is something local. Locality must be preserved at all costs. So, do you have any questions? Please ask in the comments. Thanks for liking and sharing this video. Don't forget to subscribe if you'd like to.
Really a pretty bad video. One of his worst. His name, who is Matthew O'Connor? Or Deleuze? The science of science should be as big as Vsauce. I literally was going to comment the quantum entanglement thing when I heard the clone say it at the end. I absolutely love how Nick the Ash. And then we discovered quantum entanglement. This video is about entanglement? I watch your films for about a year now, but just now when I started a class about quantum physics and chemistry, I can see how much knowledge Last time I was this early, the universe was filled. I was literally thinking about quantum entanglement. How is entanglement relevant? You seriously deserve 1,000,000 subs. 2 electrons go round the outside. As always, Nick, perfect balance. The tools are an interferometer. Okay. I love, although this was uploaded at night in my region, I still may. Okay. I miss teaching. Your channel has, yeah, he was teaching somewhere before he started the channel. I just wanted to say thank you. So, what about quantum entanglement? As I'm typing this, the clone. Okay. You explain complex. We say the magnetic field is zero. I don't know what to say. Okay, this is completely useless. A real life quantum
means that half of the light is going to go.
Delayed choice experiment. So is the Zend, the Mach Zender, is it the quantum delay? I don't know. Problem with quantum measurement. Everybody made this video 4 years ago. Understanding quantum mechanics, superposition, and entanglement. Mach Zender interferometer and wave particle duality for single photons.
Single photon interference. You know, we have talked about that in the context of the two-slit experiment. And we've learned, though, that the two-slit experiment is a bit challenging to analyze because there's so many different paths, in fact, an infinite number of paths from the source to the screen. And so we're going to redo the single quantum interference for photons using something called a Mach-Zehnder interferometer that only has two paths. And a Mach-Zehnder interferometer is very much like a color or a hardness interferometer or a Stern-Gerlach interferometer. There's a source that gets split into two paths and recombined. Okay. We're going to do this in part because we're going to use this interferometer to also study delayed choice and quantum eraser experiments. But we'll start out first by using a Mach-Zehnder interferometer for a topic that's a little more familiar, in particular, single photon interference. Okay, but before we talk about the interferometer, let's revisit and refresh our memory about the evidence for photons, right? We had seen the following scenario where we have a source of single photons, or really a source of a pair of photons, one that serves as a trigger and the other that serves as the photon under study. And in the experiment from 1986, this single photon was fed into a beam splitter and two detectors were present in the apparatus. And what we found was that if detector DR for the reflected beam fired, then DT for the transmitted beam did not fire. So the photon was only ever in one place at a given time. The anti-coincidence parameter was 0, and so we had...
Okay, this is impossible. This is just impossible.
Two-slit experiment.
Oh, something is happening here. So knowing the index of refraction n, we turn slowly the glass slide and we count the number n of fringes passing on the screen. Yeah, that's how interferometers always work. What is he turning? I don't see what he's turning. The glass slide, I don't know what he's turning.
This is a Mach-Zehnder. This is a Mach-Zehnder interferometer. It consists of a half-silvered beam splitter where incoming light is split between two paths. These two paths then lead to another half-silvered beam splitter.
Yeah, we saw this before. It made no sense. That's useless. Well, at least they're showing experiments. That's a good start. Why is this live? Oh, at least that's me. Me watching me. That's good. Always a good thing.
He invented a device that twisted because of the magnetic field created by an electric current. This was the world's first electric motor. But Faraday went.
There is a stubbornly.
The Mach-Zehnder interferometer is a device used to determine the relative phase shift variation between two collimated beams derived by splitting light from a single source. The aim of this experiment is to determine the wavelength of the laser beam and to find the refractive index of the glass plate and to find the refractive index of the air. The experimental setup consists of a diode laser and two beam splitters, two mirrors, and three plano-convex
Interesting. So the photon splits, then recombines, and goes off different paths. That's not possible.
So imagine that you have a bunch of bombs, for whatever reason, and these bombs are photon sensitive or light sensitive, which means that if you shine a... So imagine that you have a bunch of bombs, for whatever reason, and these bombs are photon sensitive or light sensitive, which means that if you shine a light or even a single photon at one of them, they will detonate and explode. But the problem is that some of these bombs are duds. Is there a way to test whether a bomb is live without detonating it? Quantum physics says there is. These two guys with really cool names, Avshalom Ilitsa and Lev Feigman, came up with a thought experiment to solve this problem using what they called an interaction-free measurement, meaning that they could test whether a bomb was live without an explosion. To understand this, we need to talk a little bit about something called quantum superposition. Quantum superposition is the theory that an object exists in all possible states at the same time, and
That's nonsense.
the act of measuring that object forces it to choose one.
No, that doesn't make any sense. You cannot. That would violate just too many ideas, too many notions. So you're telling me that an object has an intelligence and violates the speed of light. No, it's way too magical. So quantum superposition is nonsense. It's unscientific.
State. So there's a very famous thought experiment about this called Schrodinger's cat. In a box, there
Schrodinger's cat is obviously wrong. That's why Schrodinger invented Schrodinger's cat.
is a cat, a vial of poison, a hammer, a Geiger counter, and some radioactive material. When the radioactive material decays, the Geiger counter detects it, triggers the hammer to smash the vial, and kills the cat. The thing is, we don't know when the radioactive material will decay. It's completely random. So if we were to guess at any moment in time, would the cat be alive or dead? Surely it must be one or the other, right? Well, according to quantum physics, the cat...
It doesn't matter. I don't care what you're saying according to quantum physics. According to how I assume the universe works, the cat is either dead or alive, regardless of whether I know it or not. Otherwise, it just doesn't make any sense. We've never seen... I cannot imagine a cat both dead and alive. I cannot imagine it, therefore it's impossible by definition.
Cat exists in a superposition of...
No, it does not exist in a superposition. The fact that I don't know something, yeah, I don't know it. That's the beginning, the middle, and the end of that.
being both alive and dead.
No. In my mind, I just don't know. It's either alive or dead. I don't know what it means to be both alive and dead.
Remember, it exists in all possible...
It's amazing how these people can be so confused about something. I just don't understand it.
states until it is measured or observed. It is only when we open the box and take a look that the cat has to choose a state.
No, the cat doesn't choose a state. No. The cat is either dead or alive. When you open the box, you see it.
It chooses to be alive.
No, it doesn't.
Okay, so a cat can't exist in a state of quantum superposition because it's not a quantum object.
That's irrelevant. Nothing can exist in a state of superposition, period, because that would violate every premise I have about this universe. So I cannot imagine it, and therefore it is wrong by definition.
But let's take a look at another experiment which uses something called a Mach-Zehnder.
The fact that you cannot explain or cannot understand an experiment means you need to get back to work and figure it out. That's all it means. It doesn't mean anything about the universe.
Interferometer. A Mach-Zehnder interferometer consists of a light source, a beam splitter, 2 mirrors, another beam splitter, and 2 light detectors. The light source emits a beam of light and the beam splitter splits the beam exactly 50-50. The mirrors guide the light toward the second beam splitter, where the 2 beams recombine and interfere. Now the setup is configured so that the beams constructively interfere on detector A and destructively interfere on detector B.
Oh, so that's how it's designed. Jesus Christ. Oh my God.
I have an entire video which goes more into constructive and destructive interference called the double slit experiment, which I've linked in the description below. But all you really need to know here is that when the beams interfere at the second beam splitter, all of the light will show up on detector A. Detector B is left completely dark. So because of the way the setup is configured, 100% of the light shows up on detector A. Cool. But what would happen if we slowed the light beam down? Slowed it down so much that it only emitted a single photon at a time. This is where things get a bit weird. Classically, we would expect that 50%
So I don't know what it means to fire a single photon at a time. I don't know if you can do that. And even if you can, I don't know what the photon will do. I don't know what its abilities are. It might be able to go through both paths because it's a wave. It's a wavelet. It's not an infinite wave. It's a finite wave like all waves. And we know how waves behave.
of the time the photon showed up on detector A, and 50% of the time it showed up on detector B. I mean, I know we said that the light beams interfere constructively on A, but you need 2 objects to interfere with each other. So in the case of a single photon, it should show up on both detectors.
No. We know that photons in every quantum object, we know that they are really waves. So once we know they are waves, you should really stop drawing dots because you're confusing everyone. Wait. So Senna says, but it used to be considered a mathematical artifact. When did you write that? I just noticed it now. This is, oh, you wrote everything at the same time. You wrote this and this, but it is, and wait, when did you write this? Oh, this is just now. These predictions make no sense. Really? Why not? It was still about the Carl experiment. Oh yeah, okay. Yeah, but I don't care about the Carl experiment. I'm trying to understand the Mach-Zehnder experiment. Previous 2 messages were now 1. Yeah, I see the time. Yeah. This is now. Yeah, okay. Yeah, I understand. There's nothing to understand? What? Wait, I'm confused. I don't know what you're trying to say, so hold on. So this is already explained by the double slit experiment. The double slit experiment that we discovered that there is no particle photon. That does not exist. It's a wave. And it's a very big wave. It's actually sometimes bigger than the visible universe. If it's a low frequency photon, it's huge. Okay, so when you fire a photon, what is a photon? What is a photon? So I thought about this. Literally, what is a photon? I thought about what is actually a photon. We never discussed it. Let me just bring it up because I realized this, I think, this morning. Wait, you're bombarding me with messages. I can't read your messages because it's putting me to sleep. I can't read it. I'm sorry, Sinas. I cannot read it. I just fall asleep. No. Stop. If you want to join me, and you can talk. If I have to start reading, I'm going to fall asleep. It puts my brain to sleep when I read messages. Let me just show you what I think a photon is. So let's create a new thing, and I'll write what is a photon. Because Einstein wrote late in his career, before his death, he said, I still don't know what a photon is. And I don't know what a photon is, but I think this morning I figured it out. What is it this morning? What's going on? Oh, I need to tap this. Okay. So what is a photon? You're not going to believe it. So let's talk about a hydrogen atom. This is the proton. Let's put it here. So this is the hydrogen proton, and we're going to put the electron over here. Okay. So we know that sometimes something can happen that can excite the electron. So let's say that we heat up the material. And let's say we heat it up through vibration. Let's say we vibrate the material, the hydrogen gas, we heat it up. I don't want to heat it up with a photon. I want to heat it up for now without a photon. We could do it with a photon, but I'd rather not. So let's say we shake using, I don't know how we would shake. I don't even know how we can cause the hydrogen gas to glow, because that's what I want to do. I want to cause the hydrogen gas to glow. But how would I do it? So usually I think you pass a voltage through it, and what does the voltage do? I don't know. But maybe it's an AC voltage, so you're shaking it. Maybe that's causing it to glow. I don't know. I don't know how you would cause it to glow. But let's say you shake the material. Right? We know that heat is just physically shaking the material. When you heat something up, you're causing it to glow. You're just causing it to shake. You're causing the protons to shake, and the protons are shaking the electrons. And at the end of the day, the electron becomes shaken or shook, whatever, and it jumps up one level. It just jumps up. Let me do this again. It just jumps up one level. So it goes from here to there. It doesn't jump, it moves up. We know from experiments today that it doesn't skip, it doesn't transfer, it doesn't teleport from here to there. It goes slowly. We've been able to take, there is a PBS episode where they discuss it, that they took snapshots of the electrons as it was moving over to the next energy level. Okay, very nice. But after a while, for some reason, this is unstable, and the electron wants to go back to the original energy level. So at one point, it's going to drop. And as it drops, a photon is going to be released. Photon is gamma. A photon is released as if by magic. Right? This is the way they teach us. This makes no sense. Where did the photon come from? It's like the photon was inside the electron. What is this magic? This is like magic. What's going on? Okay, so what is going on? So in order to understand what's going on, what is a photon, we need to remember that a photon is a wave. Very nice. A photon is a wave. So photon is a wave. I wouldn't even say it's a wavelet. Why? And that's another realization that I had that I already mentioned. That when you see a wave in the ocean, a wave, and I would ask you, is this wave finite or is it infinite? What would you say? And of course, your answer should be, well, of course it's finite. And I would ask you why. And you would say, because nothing infinite exists in the universe. The wave is not infinite. It's on Earth. Earth is finite. So the wave is finite. Oh, so I would say very nice. So it's a quantum wave. It's literally a quantum wave. Any wave that is finite is a quantum wave. That's the definition of quantum. No, but you would say it's a little bit different because the quantum wave is the smallest wave possible. So it's a little bit different. It is a little bit different. But still, it's a wave. So the photon is a wave. It's a wave that it's a wave. And by the way, just like a wave in water that runs on the particles of the water, it's a propagation of energy through the particles of the water, so too is the photon a wave of ether. That's all it is. It's a very, very special wave of ether. It's just the ether waving. So you need to imagine that there is ether particles. It's a fluid. And that something happened when the electron moved down one level. Something happened to the ether that prompted the wave that we call the photon. Now this wave is finite. It has its boundaries, but it's just the ether waving and propagating. Not even in 3 dimensions. It has a very specific vector of motion, but it's waving through the ether. And what caused the ether to wave? Right? This is energy. So where did this energy come from? Well, it's very simple. So this electron dropped from this level to this level. And this is the bottom level. So it basically smacked against the bottom level. It cannot go any lower for some reason, which I don't know. But this is the lowest level of the electron. So as it fell, it smacked against it. And all the energy that it had, that smack, that's the photon. And that is a photon. Okay, now getting back to this experiment. So what is a photon, right? They're talking about what is a photon? A photon, there is an electron inside the flashlight or the laser beam. Inside, there is an electron. And that electron somehow was elevated to a high energy level. And then it became unstable. And then the electron wanted to drop. And as it wanted to drop, as it dropped, it smacked against the lowest level possible. And by the way, an analogy to the energy levels is a staircase. So the electron, if it falls, boom, it smacks. Or if it falls 2 levels, boom, it smacks. And energy is released. This is kinetic energy. This is potential energy converted into kinetic energy. This is very similar to a sound wave. So where was the photon before the electron released it? So the answer is the electron never released it. The electron didn't release a photon. There's a system. The system was in high potential energy. And the potential energy was converted to kinetic energy. And that's it. The electron went down 1 or 2 or multiple energy levels. And that is the conversion into kinetic energy, just like anything else that we know in the world. So you're beginning to see how the quantum world is completely mechanical. It's a completely mechanical world, and you can definitely visualize everything that these quantum particles do. You can slowly understand exactly what they do. They're very simple. These are once you understand everything they do, it's very simple. And this is not the most foundational level. The most foundational level is the ether, the particles of the ether. Whatever laws govern the interaction between the particles of the ether. Everything I'm talking about, these are just artifacts of the interaction of the particles of the ether. The motion of the photon is just the propagation of energy through the ether. And I'm not even saying something, I'm saying ether. Everyone else, they say, oh, it's the electromagnetic field. Yeah, okay. You can call it multiple word names. That's fine. It's the ether. It's just the ether. It's fine. There's particles of ether, and there's propagation of energy through these particles. And that's all it is. It's a mechanical universe. Congratulations. That is locality. Locality is that the photon, everything I'm telling you, it's a mechanical explanation. Everything in quantum mechanics is a mechanical explanation, just like the name suggests. It's a completely mechanical explanation. It's a very simple explanation. So that's a photon. This is my revelation of the day. So if I keep having these daily revelations, I think before long we'll understand literally everything in the quantum realm. Like, I don't know why there is this what creates this bottom level? Why? What is it smacking against? Oh, you're writing? Oh, you're sending text messages? Whose channel is this? No. No, I don't think so. No. Biographing. No. Unfortunately, people that believe in the things that I believe, I think they're losing their mind. Mm.
Okay, so let me bring in Eric.
Wait. This is a 6-hour podcast.
Eric Ryder. Eric, welcome, sir.
Very nice, thank you. I hope you can see my screen share.
I can, so I have that up now, and you are in control of that, sir, because you uploaded it. So what I will do is I will take myself out, hand things over to you. And you have, so I guess we could describe this as an independently developed theory, right? And so
that's correct.
Running us through that.
Independent experiment and theory.
No, I don't challenge quantum mechanics. No. I just interpret quantum mechanics. I don't challenge it. If they're challenging it, then they're my enemies. I'm going I'm completely mainstream. I'm not challenging anyone.
Well, thank you so much. Thank you so much.
Yeah, well, thank you, Tim. So it's a serious challenge to quantum mechanics. And these lecture slides are rather detailed, but I implore people wanting to dig in and see what I'm doing better to get the PDF of it. And everything about what I'm doing is available on my Threshold Model website. So my challenge to quantum mechanics is by history, theory, and experiment. But this lecture emphasizes the experiment, which looks something like what's here on the screen. So as far as the history, it's important to know that someone will say, well, what about such and such effect and whatever? And so I've handled quite a bit of it, but it's in another lecture that I have prepared. But this one, as I say, is emphasizing the experiment. So this passage is the best I've been able to find about the wave-particle paradox and the photon model. And by Bohr in this book, which is about the Einstein-Bohr debates. I'm going to read this.
I would say Bohr is the last person you would want to talk to, listen to. Einstein basically, I think Einstein felt Bohr as a friend because Bohr was half Jewish and was anti-Nazi, and that was the foundation of the friendship. But I think Einstein really tried to explain things to Bohr, but Bohr was into magical thinking. I mean, Bohr, there was a quote. I saw a quote from Bohr that he said, we should give up on conservation of momentum. So obviously Bohr was nonsensical. So I was actually listening to Bohr's grandson, who researches life extension, which is fine. He's a professor. And I'm trying to figure out, how did Bohr end up being such a lunatic? Because Einstein was trying to help him see the world and was basically hopeless.
Sentence. If a semi-reflecting mirror is placed in the way of a photon, leaving two possibilities for its direction of propagation, the photon may be either recorded on one and only one of two photographic plates situated at great distances in the two directions in question, or else we may, so this is part two, there's two parts, by replacing the plates by mirrors, observe effects exhibiting an interference between the two reflected wave trains. So it's a two-part model, and Bohr explains straight away that it's no way to visualize this idea. And so I'm saying the best way to handle it is to understand that this is a model and that the photon is not a thing. It's a paradoxical model from the very beginning.
Yeah. Bohr believed in magic. Bohr was into magic. He was, before he got married, he was a member of the church, whatever that means. So I think he was religious. And I think he was driven, he never abandoned his religion. And I think the religion infected his mind, and he was a lunatic. He was not scientific. So I don't think we should consider Bohr as anything. I think we need to basically ignore him. Whatever he gave us is nice, but he's gonna confuse you. If you listen to Bohr, you're gonna end up being confused. So I don't recommend it. By the way, why did she not respond? Oh, she did. Oh, 23 minutes ago. Why did I not hear it? Um, okay, let's hope she'll call. A very pretty girl. So, yeah, I mean, you're listening to Bohr, you're going to get confused.
But it does seem to be consistent with the experiments that say things work that way. But I'm going to show that it really doesn't work that way. So the realization of this passage is like I drew out here. Other experiments have done this. There's a particle part, which is a beam splitter. They use detectors. The detectors make pulses, and they try to see the timing between the pulses. The idea is that energy is supposed to be quantized such that their photon energy will magically deposit itself one way and not the other. This is a form of entanglement. It's a one-particle entanglement. The other part of the photon model is that you leave it on over time, you collect a bunch of pulses, and you can see an interference pattern. So we're going to show that it's this first part of the model that fails.
So anyway, I was going to say, oh, she's calling. All right, we have to end it here. Let me cut the stream. I'll be back.